Hello, today we're going to look at an application of what we've learned about expectations so far to come up with an estimator or a predictor. So the situation is that we have some value, a random process that we can observe, and that random process is x. So we make an observation of x and we call our observation x hat. And we want to come up with an estimate of another random process, y. So in this case our estimate will be y hat of n. Here in that I've just highlighted, we assume that these two random processes are related to each other in some affine linear sense. In other words, we assume that y is equal to some constant alpha times x plus beta plus, in this case, some noise. So x we're going to assume is zero mean, just to make things simpler. We could do it non-zero mean, but that would just be more work. We don't know this relationship exactly. We don't know what alpha is. We don't know what beta is. And we're going to assume that the noise is zero mean. This is, by the way, kind of a special case or related to what goes on with adaptive filters. In adaptive filters, you're not just estimating or trying to figure out just a linear relationship, alpha x plus beta type of a thing. Instead, you're estimating a whole filter where alpha would be a vector and it would be multiplied by x at different lags. But the process is very, very similar. So this is a good place to start. So in this particular thing, we're going to assume, or we're going to use an estimator that is y hat is equal to c x hat plus d. So you can see that we're closely related to what we have before with y. Okay. Well, we have multiple steps to do this. You might guess, and I'll tell you ahead of time, little spoiler here, correctly, that we want c to be the same as alpha and d to be the same as beta. But remember, we don't know those yet. So, step one, let's find beta. We'll be using this later on. So this is pretty straightforward. We just take the expectation and we're going to assume that we can actually find these expectations. And I'll talk later about what we do if we don't have, say, the PDF given to us. But this is going to be the expectation of alpha xn plus beta plus our noise. The noise is also uncorrelated with x. Doesn't matter here, but it will later. So we get alpha times the expected value of x plus expected value of beta is beta plus the expected value of the noise. And from above, we know that x is zero mean, noise is zero mean, so we just get beta. So the expected value of y gives us our beta. We can't do anything with it yet, but that's a good start. 2. We need to place some constraints to decide what is a good estimator. Well, the first constraint we'll do is we want an unbiased estimator. To get an unbiased estimator, we say that the expected value of y minus our estimate, y hat, given x hat has to be 0. Okay, so let's run through that. The expected value of y is going to be alpha xn, and this is given x hat, so we've got our x hat in there, plus beta plus u of n minus c x hat n minus d. We want that to be equal to 0, but let's go ahead and push through this computation. Well, that's equal to 0 by definition. And the expected value of x hat is going to be 0. So what does this tell us? This tells us that we want beta minus d to be 0, or in other words, beta, or d equals beta, which is equal to the expected value of yn. Okay, so we're partway there. We have now, for our y hat is equal to cx plus d, we've come up with the correct value of d, which is equal to the expected value of y. Next, let's come up with another constraint. We would like to minimize the error of our estimate, the error energy. And so for this, we're going to have expected value of yn minus y hat n squared. Now, if these were, complex, it would be y minus y hat times y minus y hat conjugate. But just to simplify notation a bit, we'll just do this. Okay, so this is equal to the expected value of y minus cx n plus d squared, and using the FOIL method that we all know and love, we get expected value of yn squared minus 2 times the expected value of y n times cxn plus d plus the expected value of cx plus d quantity squared. So we've already constrained d to be beta, and that constraint came from the desire to have an unbiased estimator. So now, to get the correct c, we're going to do our traditional quadratic minimization by taking the derivative with respect to c. And setting that equal to 0, differentiating with respect to c. Okay, so we'll call this equation 1, so I don't have to type it all out again. And we get the derivative of 1 with respect to c is equal to 0, which is equal to, the first term has no c in it, so it goes away. The second term has one c in it, but we can multiply this through. So we're going to get 2 times the expected value of yn xn, and that was multiplied by c. So the derivative with respect to c, it goes away. The second part, the expected value of yn times d, has no c, so it's 0. And then finally, we have this last bit here. That's going to be plus 2 times the expected value, use our chain rule here, xn times cxn plus d. And there we go. Well, this simplifies rather quickly here. We need to do just a little bit more though. So this is going to be negative 2 times the expected value of yn xn plus 2, and let's divide up this last expression, times the expected value, we can pull the c out, of xn plus 2 times the expected value of xn times d. Well, expected value of xn is 0 because x is 0 mean. And recall we're setting that equal to 0, which implies that we have c is equal to the expected value of yn xn over the expected value of xn xn. Okay, so now we have a value for d. D is equal to beta, which we find from the expected value of y. And c is equal to the expected value of y times x divided by the expected value of x times x. And we have our minimizer. But let's close the loop on this. So far we haven't explicitly found alpha. Turns out we don't need to. But look at this. As you recall, the expected value of yn xn could be written as alpha xn plus beta plus u of n, all times x of n. This is going to be alpha times the expected value of xn plus beta times the expected value of xn plus the expected value of un xn. Well, right away we can get rid of that. It's 0. But what about this other term here? If we assume that u of n and x of n are uncorrelated, in other words, the noise isn't a function of the signal x. And this is a very reasonable assumption. Then we get this. And that's 0, and that's 0, so it disappears. So now we get this is equal to alpha times the expected value of xn, xn. When we plug that into the equation for C, C is equal to now alpha times the autocorrelation of x at point nn. Those two divide out, giving us alpha. So C is equal to alpha. So now we know alpha. We have our optimal predictor, and in terms of one that gives us the lowest prediction error, expected prediction error, and it's unbiased. In other words, the average value of our prediction error is going to be 0.